All right, so let's continue discussing A-stability. So before, it's like we derived what is called the stability polynomial, which is what happens when you apply a Runge-Kutta method to a model differential equation, y prime is equal to lambda y. Okay, and then now let me state a lemma. So this is lemma 4.1. Okay, so it says for every Runge-Kutta method, there exists some polynomial r in the space of, well, rational polynomial, okay, of polynomials of degree s for the numerator and denominator, okay, such that yn is equal to this rational function, okay, of h times lambda to the nth power, and n goes from 0, 1, and so on. Okay, and moreover, if the RK method is explicit, then R is actually not just a rational polynomial, but it's just a polynomial of degree s. Okay, so let's try to prove this. Okay, so we already know we have an expression of this form for relating the new solution. It's like with the old solution, so it's just going to be some multiplicative factor, if you will, which depends on h lambda. Okay, so it remains to show basically that this object here is actually a rational polynomial, a rational function. Okay, and so let's just see what happens. Okay, so so you can define this R of z, right, to be just 1 plus z b transpose, the identity minus za inverse acting on this vector of once. Okay, and then z is some complex number in general. All right, so it remains to check. I guess I should also say that the reason why you just have this is because, if you recall, it's like in the model problem we looked at, y at time 0 is just 1, and so it's like y0 is 1, and so when you have a recurrence like this, you just get this rational function to the nth power. Okay, so you just need to show that this function r of z, right, is indeed an element of the rational functions with degree s. It's like for the numerator and s for the denominator. And then if you're in a situation where it's explicit, it really just is a polynomial of degree s. Okay, so so let's look at this. Okay. So of course, it's like the main part one has to be mindful of is this inverse term. So let's look at what happens with the inverse term. So if you look at the identity minus ZA inverse, you can basically write down, it's like the explicit form of this in the following way. So this is the adjugate, the j of the identity minus ZA divided by the determinant of the identity minus ZA. Okay, where the adjugate of a matrix C, right, the adjugate, or sometimes referred to as the adjunct, right, is the determinant. Well, okay, I should say that where the adjecate has components, has sort of ij components, right? Which are given by the determinant of the sort of J-if principal minor, right, multiplied by a factor by minus 1 to the I plus j. Okay. All right. So let's think about this. So if you look at the entries, it's like of this matrix, identity minus ZA, right? Each of these entries is a is linear in Z, right? So each entry of the identity minus ZA, right, is linear in Z. Okay, so each element basically of this adjecate of that matrix, then up to a sign, is a determinant of a S minus 1 by S minus 1 matrix, right? Okay, so each entry in the adjecate of this matrix I minus ZA, right, is the determinant of a S minus 1 by S minus 1 matrix. So that means that this adjecate of the identity minus CA is an element of the polynomials of degree up to S minus 1 in Z, if you will. Okay? All right. So and then we also know that the determinant, right, of this is obviously in polynomials of degree S in Z. Okay, and then the determinant of identity minus ZA is an element of the polynomials of degree S in Z. All right, so now you have this term, which is this term here is an element of the rational functions of degree S minus 1 and S. S minus 1 in the numerator, S in the denominator. There's another factor of Z out there, so this whole thing is a polynomial, or sorry, a rational function. It's like of degree SS. Okay, so so this implies that R of Z is in the space of polynomials of degree SS. All right, and then you can ask, well, what happens if you have that the Runge-Kutta method is explicit? All right, so let's see where we go with this. So let me just write this all out for you one more time. Right, so you have RZ, which is equal to 1 plus ZB transpose identity minus H lambda, well, ZA. Inverse acting on this vector of 1s times, well, without yn. All right, so this thing here is an element of the rationals of degree s minus 1 s, right? This is in a polynomial of degree s, right? So the product, well, sorry, polynomial degree 1, right? So the product of these things implies that this is a polynomial of degree, or rational function of degree ss, okay? All right, and then finally, it's like what happens if A is, or the Runge-Kutta method is explicit, right? So if the RK method is explicit, this implies that A is strictly lower triangular. All right, and if A is strictly lower triangular, that means that the determinant of the identity minus ZA, right, is just going to be 1, actually. Okay, and then you know the adjudicate of 1 minus, or the identity minus ZA is a polynomial degree s minus 1. Okay, so that means that you have RZ is now 1 plus ZB transpose identity minus ZA inverse times this vector of 1s, right? And then if A is lower triangular, then this inverse is no longer a rational function of degree ss, but it's now just a polynomial of degree s minus 1. This is a polynomial of degree 1. So that means the whole thing then is a polynomial of degree s, which is what we wanted to prove before. Okay? All right. So just with this observation alone, we can say something then about the astability of explicit Runge-Kutta methods. Okay, so let me just state the lemma. So 4.2, right? So let's suppose that applying your numerical method to y prime is equal to lambda y, right, produces, and I should also say y at 0 is 1. So this produces a geometric solution sequence yn is equal to r h lambda to the nth power, right? Then the claim is that the stability region D has the form of Z in the complexes such that the modulus of RZ is less than 1. Okay, so this is the stability region, if you will. It's like associated with a method, it's like with a certain stability polynomial. And this really just follows from the definition, if you will, of this stability region. And then a corollary of this is that no explicit Runge-Kutta method can be astable. And why is that? And that really sort of comes from the observation, if you will, that the stability polynomial for an explicit Runge-Kutta method R is a polynomial of degree s. Okay, So the proof is that if you're given an explicit Runge-Kutta method, right, R is a polynomial, it's not a rational function. Okay, and then you can check that because R of Z is equal to 1 plus ZB transpose identity minus ZA inverse acting on this vector of 1s, right? When you substitute Z equals to 0 to this, right, you get 1. Okay. And so the problem is that all right. So the problem is that no polynomial except for the constant function may be uniformly bounded by the value unity in the negative complex half plane, and that implies that you don't have phase stability. So this excludes phase stability. All right. So again, the basic bottom line, if you will, is that if you have an explicit Runge-Kutta method, then it can't possibly be astable.